Good morning. Today's lecture, we will go to the last topic, which is state reduction and assignments. So what does state reduction means? Most likely, as we know, when we do any design, we need to convert this from verbal problem into a states or into a flow chart. Then we can create a states. Then these states will determine the number of flip-flops that are required. So for the sequential circuits, the number of flips, the relationship between the number of flip-flops and the states, like 2 power number of flip-flops equals to the number of states. So if we figure out there are too many states, then this means a lot of flip-flops. This means increasing in the hardware complexity, increasing also in the cost, increasing in the energy consumed by the digital logic circuit design. Therefore, our target is to make as minimum states as possible so we can reduce the cost, we can reduce the complexity, we can reduce also the power consumption during the IC. How can we achieve this? By looking at the states and monitor, is there any states are in common, or is there any states that can be replaced? That's what's called state reduction, which is try to remove the number of states and achieve the same job, achieve the same outputs without worrying the same output, the same requirements, by doing the minimization. It's very similar to when we discussed the K-maps, or when we discussed the Boolean algebra. We said that the function can be very long, and we make it a shortcut to be a small one, like using Boolean algebra theorems and postulates. Or when we use convert this to canonical form. So in canonical form, it is, yes, unique, but it's not minimized. Then we minimize it by using K-maps. Then here in the states, if we can have a function with a large number of states or a program, but sometimes we may or we may not do the state reduction. So it depends on if we can I do it or not? It depends on then many factors. So how can we achieve this? That's what we expect to see today. So basically, when we reduce the number of states, results reduction in number of flip-flops. And this is a great advantage. Reduce the number of states, reduce number of flip-flops, reduce complexity, and instead of assigning, for example, when we have 5 states or 6 states, we need to assign A, B, C variables. But when we have 4 states, reduced to 4 states, we can assign only 2 flip-flops instead of 3 or something like that. So let's assume that you have 4 states, so 2 power 2 equal 4. Then in 4 states, you need 2 flip-flops. If you have 6 states, 2 power 3 equal 8. So from 8 you can use 6. Therefore you need 3 flip-flops. So even if you figure out from reducing 6 states to 4 states, this means less hardware, less cost, less energy consumption. How can we achieve this? How can we make sure if we can do that or if we cannot? Look at this diagram. Sorry. Look at this diagram. Assume the initial state is state A, and we have the following input sequence: 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0. So we are with state A, and the input is 0, therefore the output is 0. Then we're remaining at state A. Then after that, since the input is 0, the next state is A. Then after that, if the input is 1, the output is 0, then we will go at B. And so on. So here is A, Here is A, input 0, output 0, input 0, output 0. Next state is A. Then the input is 1. If the input is 1, the output is 0. The next state is B. Then in B, if the input is 0, the output is 0. Input is 0, output 0. The next state is C. Here is C. And so on. You know how to do it. To keep the following at the end. Now, what the state reduction says, we can say these two states are equivalent at the following condition. I can summarize them here. The procedure. So there is the first procedure by inspection. So by inspection, do the following. Look at the outputs. Of each states. If they are the same outputs, continue. If not, then of course they are not equivalent to each other. If they are the same, continue. Then number 2, look at next states for each input. Then if they are, we have two conditions. If they are the same, which means same outputs, same next states, then they are equivalents. Then if they are not, there are still some other thing we need to check, which is it the same as states itself or other states, other compared states? If yes, then they are equivalents. If no, then they are not equivalents. So the first thing, look at the output. Then after that, look at the states. Let's make a comparison and look at this state table to try to follow this procedure. The first observation, look at the outputs. Here is the outputs. So you'll see here 0, 1, 0, 1, 0, 1. Therefore, we need to compare between A, B, C. There might be some of them can be equivalent to each other. There might or might not. While for the other outputs, here is 0, 1, 0, 1, 0, 1, 0, 1. Then D, E, F, G, they might or might not be equivalent to each other. So this is methods called by inspection, which is basically you need to inspect to look each pair. So now we just say, like, first group, we need to compare these 3. The second group, we need to compare these 4. Let's go back to the first group. So state A between A and B. State B between C and D. Is there any similarities? No. Then there is no way to A and B will be equivalent to each other. So we cannot say. How about A and C? So A with A and D, C, A and B, C with A and D. Do you think they all are equivalents? Equivalent in A, but there is B and D, which will make it unequivalent. So they are not equivalents. Then next, look at B and C. So here is C and D, here is A and D. So here, C or D and D, they're fine. C, which is the same as the other state, it can be fine. But A, it's not the other state. It's not B or it's not C. Therefore, they are not equivalents. Again, with this side, they are fine. But with this side, with this side. This is C, this is A. When you look at C, it's not the same as the state B. I'm sorry. But it will be the same as state C. So it can be okay. But look at A, it is not the same as B. Or it's not C. If it is B or C, it can be okay. Then it is not. Therefore, B and C are not equivalent to each other. Then we can say, in the first three groups, they are nuts. On the first, three states, we cannot say they are equivalent, so there is no state reduction. That's why we say it sometimes may or may not. Because the reason sometimes we cannot do it, because they are not equivalent. This is the simplest that I can have. Let's look at D, E, F, G. Let's look at D and look at them here. F. Here is at F, 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 F. So they are common in F. Then here you see A, A. Therefore you can realize that E and G, between A and F, and the output, they are the same. So we can say easy that E, G are equivalent. E and G are equivalents. So we can say it seems that this state has been repeated, or we can simplify it. Since they are equivalent, we can say assume G equal to E. Every time in anything in this table, when you see G, make it E, then erase G. Erase it like it's not exists. G equal E, then erase G. Eliminate G like it's not exists. So what I'm going to do, I'm going to redraw this table by erasing G. And what we will do, we will erase this, and every time we see G, we will make it E. Here, is there any G here? This is the only G, we'll make it E. Okay? That's the idea of the state reduction. Erase G, and in other states, make G equal to E. Then let's redraw the circuit, redraw the diagram, then we end up by this one. A, B, C, D, E, F. There is no G, no longer G, and it was G in the past, now it's called E. After doing this simplification, don't stop. Check, is there any other possibilities that we can achieve? How? Let's make other observation. They look at the inputs and the outputs. Here is 0, zeros. Then we need to look at this and look at the other side, which is here 0, ones. Then we can monitor this. So let's look at state A. Can we achieve A and B? I don't think so. A and C, no. B and C, no. Let's look at the other side, which is D, E, F. So those are F, this is E, this is E. So as a result, we can say D and E are equivalents. Does this make sense? Because they have the same E, F, E, F. Then here 0, 1, 0, 1, right? Then they are equivalents. So what do we need to do? Let's assume D equal F and eliminates F. Or actually, let me make it F equal D. F equal D and eliminates F. So we will just eliminate this row. Eliminate this row. And whenever we see F, we will replace it by D. So this one will be D, this one will be D, and that's it. That's how we got this one. So we have these states. Now, can we simplify it more? I don't think so. That's all. You can try different ways. So This is D, this is E. Yes, this is the same way here. This is D here, that's fine. But this is not the same way, so we cannot simplify it. So that's the simplest way. Then if we need to draw the state diagram for this part, I can draw it like this way. Here is state A. Then here is B. If A is 0, we will remain at A, the output is 0. If A is 1, we will go to B, and the output is 0. Then B, if it is 0, we will go to C, and the output is 0. C, if it is 1, it will go to D. I forget B when it's 1. B, when it is 1, it will go to D. The output is 0. C, when it is 0, it will go back to A. While C, when it is 1, it will go to D. D, when it is 0, it will go to E. The output is 0. D, if 1, will remain at D, and the output is 1. C, if it is 0, it will go to A, and the output is 0. If it is 1, it will go to D, and the output is 1. Now, let's test the sequence that we got in this one, this sequence. So our target is, after we draw this state diagram, I mean, it just like this is just a proof. I mean, you don't need to do it every time. I mean, it's just like if you do the final state reduction and that's it. But I mean, here we need to validate that to make sure, are those the same or not? After removing two states, which we make it more simpler, are those the same or not? So we should give the same input sequence, start with state A, then we will see what will happen. So here is state. We will start with state A. Here is the input sequence. Here is the output. So the input sequence given was 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0. Now let's follow the diagram. So here A with input 0, A with input 0, output is 0 and remain at A. Output is 0, we will remain at A. Now A, input is 1, we will go to B and the output is 0. So we will go to B and the output was 0 here. Now B, the input is 0. B, input is 0, we will go to C and the output is 0. So the output here is 0, we will go to C. C, input is 1. Here is C, input is 1, we will go to D and the output is 0. So here the output is 0, we will go to D. Now D, the input is 0. Let's go to D, input is 0. We will go to E, the output is 0. So we'll go to E, the output is 0. Here's 0, we'll go to E. E, the input is 1. Here is E, input is 1, output is 1, then we will back to D. So input is 1, make output 1, we will go back to D. Now with D, input is 1, here is D, input is 1, we will remain at D, output is 1. Remain at D, output is 1, remain at D. Now D, input is 0, let's go to D, input is 0, output is 0. And we will go to E. So output is 0, then we will go to E. E, input is 1. Here is E, input is 1. The output is 1, we will go to D. So the output is 1, we will go to D. Then D, the input is 0. Here is D, I'm sorry. The input is 0, output is 0, we will go to E. And the output, again, is 0. Output is 0, we will go to D. Then D, input is 0, we will go, output is 0, we will go back to E. Output is 0, go back to E. Okay? So that's, okay, we forget E, input is 0, E, we will go to E. E with input 0, here is E, here is input 0, we will go to A, and the output is 0. So here is the output is 0, we will go to A. So the next state A, and that's it, because there is no other sequence. So by looking at the sequence, it will be as states. Sequence will be A, B, C, D, E, D, D, E, D, E, like this. And look at the outputs, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, like this. So we need to compare this between this one and the original before the reduction. That was how it was before the reduction. Actually, also I did the analysis like this way here. So this is already written. Look at the output sequence. Let's make a comparison. 0, this is original, reduced, this is the original. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 0, 0, 0, then that's fine. We don't need to worry about it, right? Then let's look at the states. Is it the same sequence? A, B, B, C, C, D, D, E, E, D, F? Oh. Let's recall from our reduction, we already said that G and E are equivalent, D and F are equivalents. We replaced F by D, we replaced E by G. So whenever we see F, make it G. Whenever we see E, make it D. Or so D is actually equivalent to F, then we can say that's fine. D is equivalent to F, then we can say that's fine, right? E is equivalent to G, then that's fine. D equivalent to F, then that's fine. E equivalent to G, then that's fine. A. Therefore, they're equivalent. So the sequence sometimes, if it looks like difference, this is because you haven't substituted the originals or the reduction. If you substitute the reduction, then it should be the same. So same output, same inputs. Therefore, we can say this reduced model is the same as this old model. Those are equivalents. But this one requires a lot of hardware. This one requires less hardware. This means, again, less cost, less energy consumption, faster time as well, and less complexity. So when you do the design, it will be less complicated. That's why, therefore, during designing digital logic circuits, one of the steps, which is try your best, is to reduce the equivalent circuit. That's in practical problems. Try to reduce the number of states possible. to make it less hardware. So we don't want to spend a lot of money, spend a lot of time, a lot of effort, and even like the design will be kind of poor because it will be slower, while the reduce will be faster, much faster. Okay? Does this make sense? Any question? So that's the idea of making the state reduction, and that's why I showed you how we can do the state reduction on after doing the state reduction, we are still able to finalize everything, and we are still able to achieve the same job, even if it is being reduced. How we can do the state reduction? Two ways: inspection and implication table. The inspection, as I showed you earlier in the last example, implication table, it requires some procedures. Let me talk a little bit about the inspection, discuss more about the inspection, then we'll go to the implication table. So we need to make a state reduction. The first observation, if it is written in either any table, you can look at this, look at the outputs and see. So for this example, look at the output 0, 1, 0, 1, 0, 1. Then look at the other one, which is 1, 0. Therefore, since state C between 1, 0, which is different than the others, therefore there is no way to make any state reduction with state C. We cannot say that. After that, look at other states, which is state A and B. A and B, A between B and C, B between C and A. Then there is no way to do any state reduction. Look at B and D, B between C, A, D between A, D, A. So, C, C, A, they are the same. Then, since they are the same, they are equivalents. Therefore, we can replace D by B. Whenever we see D, make it B. Let's redraw the table. Then it's going to be A, B over 0. So here just it was D. Now it will be replaced by B. Then and erase D. The same way that what we did before. Okay, clear? So if you know the procedures, it will be straightforward, like within 1 minute, 2 minutes you can do it. But make sure to understand the procedure very well. Look at the outputs, then look at the states. Let's look at this example. Look at the outputs, 0, 1, 0, 1, 0, 1. Okay, which is fine. Now, C, we realize 1, 0, then we cannot do anything with C. Look at states A and B. Look at A and B. A between B, B, which is fine. A, the other part, which is C, A. Now, let's look at C, look at A. A, it's not the same as state itself, but it's same as the other state. Then we can say, okay. Look at C. Is it the same as the state itself? No. Is it the same as the other states? No. Then there is no way to do it. So we cannot say A and B are equivalents. A and B, there is no way to be equivalents. That's how we make the inspection. Let's look, monitor B and D. B and D, it's between states A, which is fine. Then look at D, look at B. Here, is it the same as the state itself? Yes. The same as the state itself? D and D? Yes. Then B and D are equivalents. Are equivalents. So what I'm going to do is replace D equal B and eliminates D row. So I'm going to redraw the table. States. Here is X, here is 0, 1, A, B, C. No longer D. Then, let me put the output over 0, over 1, over 0, over 1, over 1, over 0. Now this is B, C, B, A, D, B. Oh, remember, we just said that we replaced D by B, right? Therefore, we will not write it as D, write it as B. That's the difference. Okay. Other question. Now, it's your turn. Try it. Let's see. What do you think? Which states are equivalents? Is it AB, BD, or AD? Let's look at B and D. Okay. Between D, B, this is AA. So with AA, they are correct. D, it's not the same as state B, but is it the same as the other states? D? Yes. B here, it's not the same as the state D, but is it the same as the other states? Yes. Then we can say, yes, they are equivalents. Then we can replace B by D. And it's up to you. You can say B equal to D, or you can say D equal to B. So if you want to erase the state B and keep D, that's fine. If you want to erase D and keep B, that's fine. What I'm gonna do here, I'm gonna do the other approach, which is in the past we used to erase B, erase D. Now I'm gonna erase B, I keep D. Again, it's up to you. Here is X, here is 0, 1. Then here is A, B, and I'm gonna erase B, so A, C, D. So with A, it will be B over 0. Since there is no longer B, it will be D over 0. Then here, C over 1, C, D over 1, B is no longer exists, so it's gonna be D over 0. Then here, for D, B over 0 is no longer, B is no longer exists, it's gonna be D over 0. Then here is A over 1. So we see we did a lot of multiplication, a lot of simplification, so there is eliminate B, like B does not exist. Then we can reduce the states. Now we have 3 instead of 4. Then less hardware, faster program, and easier way, less complicated, less energy consumption, less cost. Any question about the inspection? So we see the inspection when we have a very small states, number of states, very small state table, then that's fine. We can do it by inspection. How about if it is complicated? How about if we have very large tables? Doing the inspection, if it's being very large, this will make it harder, more difficult, and more. Then you need to have a guess, or you need to look at, make this one and this one and this one and this one. So you will get an error, or like your chance to have an error will be high if it's very large. So how can we do it if it is very complicated, or large number of states, large number of outputs, large number of inputs with very large programs? Then there is another way. Number 2 is by implication table. Implication table, again, is basically used for complex states, which is when it is very large table. That's what's been used for when the inspection is very hard to apply. When you have, like, for example, 10 states or 12 states with 4 inputs, which very large table, then how can you make sure you compare between this will take it so long time. Therefore, the implication table is the best. How to do the implication table? Here's the procedure. So step number 1, list all the states except the first states in vertically, while horizontally, all states except the last. So we can get all possible combination between the states. What does this mean? Let's assume we have states from A to E, which is states A, B, C, D, E. So in order to produce that table vertically, let's forget about the first state A, then let's draw B, make us a row, C, D, E. Then horizontally, all the states except the last. So we will say A, B to C. Here is A, B, C, D. Okay? Does this make sense about the sequence? Vertically, all of the states except the first. Horizontally, all of the states except the last. Yeah? Fine? Now, we are ready to draw the table. How does the table looks like? It will be like this. It will look like this. So you need to know how to do this, of course. That's how we make, let's say, like all of the possible combination between the equivalence can be achieved, or can be of the possibility can be between this, using this table, which means we can, or possible between A and B, or A and C, or A and D, or A and E, or B and B, B and C, B and D, B and E, or C and B, and so on. So we will not go to the point such that A and A, because it's infeasible. That's why the table looks like this way. So we will not get the same state repeated. You will not say a comparison between A and A or B and B and so on, because we have this implication table like this way. Okay, clear? Now, with this one, we need to look sure to make, or to say like, this is all of the possibilities. We need to cross or eliminate the elements that we guarantee, or we make sure that they are not exactly the same. So basically, what we will look all the possibilities, cross out cells to those pairs of the states. The output are not equal to the inputs. So you will look at the output and the input. Let's assume between the output and the input of A and B are not equal to each other, then I'm going to cross this one. Then A and C are not equal to each other, cross this one. A and E not equal, cross this one. B and C are not equal, cross this one. Then cross this one. Something like that we can cross. The remaining blocks, we can say there is a chance, or there is a possibility for these states to be equivalent. Therefore, these states, we can look at the states of the next states for the remaining blocks that uncrossed. For the next state, the empty cells that are not crossed, those we can create something called implied pairs. Basically, we need to look at these pairs and make sure, look at the next states for each one. Does those have the same next states? If yes, for all of the inputs, then we will put a check mark, which means they are equivalents. If no, here is the points, which is we need to worry about what will happen later. Then we will create something we call implied pairs to determine what are the pairs that we can have to remove this. Then, if there is implied pairs that cross here, it will be eliminated. After that, we can eliminate what are the implied pairs that are uncrossed. How we can do this? I think with the example, it will be much easier to follow, better than like reading the notes. Now we have states A, B, C, D, E. So in order to do it, let's do the table, like do it vertically and horizontally. So according to step number 1, to implement the table vertically, remove the first state, so it will be B, C, D, E. Horizontally, first remove the last state. So start from A, B, C, D. Okay? Do you agree with me? Now, let's construct the table. This is the first one, second one, third, fourth. Now, we're done with step number 1. Step number 2, look at the outputs. I'm going to redraw the table just for monitoring. Actually, you don't need to do it. You can just look at the outputs and do it, but I'm going to do it here for demonstration purposes. So I'm going to make states. Here is X, 0, 1. Here is A, B, C, D, E. Basically, I'm going to redraw that table by inserting only the outputs without worrying about the inputs. So the outputs here, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1. Okay? So do you agree with me on this table? Now, let's look at, make a comparison between A and B. Are those sharing the same inputs? Yes. The input, the same output? Yes. So don't cross this one. Don't cross A and B. Let's look at A and C. here is A, here is C. Are those sharing? Yes, those are sharing. Then don't cross it, because they are the same. Then A and D. Here is A, here is D. Are those the same? No. Therefore, we will cross this. Now then, A and E. Here is A, here is E. Are those the same? No, then cross it. So the same way we will apply it for B. Now, B and C. Here is B, here is C. Are those the same? Yes, don't cross it. B and D. Here is B, here is D. Are those the same? No, so cross it. B and D. Now, B and E. Here is E, here is B. Are those the same? No, then cross it. Then let's go to C and D. Here is C, here is D. Are those the same? No, so cross it. Let's look at C and E. Here is C, here is E. Are those the same? No, so cross it. Then look at D and E. Here is D, here is E. Are those the same? Yes, so don't cross it. Then now we're done with step number 2. So how many boxes we have left? 4 boxes or 4 squares, right? So step number 3, I'm gonna redraw this table, but now I'm done with the outputs. Let me look at the states alone. Again, actually, when you do this design, you don't need to draw the table. You can compare like this and this table. But I did here just again for demonstration purposes. So for step number 3, I'm gonna redraw the table. Here is the states. Here is X, 0, 1, A, B, C, D, E. Then with state A, it will go to here CB. State B, it will go to CE. State C will go to BE. State D will go to DE. DB, I'm sorry. Then here it will go to EA. Okay, so what should I do in step number 3? Step number 3 says that, look, how many squares remaining? We have 4 squares, right? I'm sorry. Wow. Apologize. I need to make it. I used to make it in airplane mode. Okay. No worries. We have 4 squares. Four squares are not crossed, right? What are these squares? A and B, right? This one, A and B, A and C, B and C, D and E, right? So again, I'm gonna write them here. A and B, A and C, B and C, and DE. Okay? So what I'm gonna do is to look at each square, look at each pair, A and B. Let me look at A and B. A between C, B. B between CE. Right? So look at the first one. Here is C, then that's fine. But here we have B, we have E. Okay, so what I'm gonna do, BE, since they are causing the problem, if they are the same, then they will be equivalents. Those are causing the problem. So I'm gonna call it BE. This is it's called implication pair. Implication pair. So what I'm gonna do, I'm gonna go to this box here. I'm gonna write BE, which indicates that the main reason for this blocks is not being equivalent is the existence of BE. If they are equivalent, then problem done. Okay? So this is the first block. Let's go to A and C. Here is A, here is C. A between C and B, C between B and E. So we will see that both are also main reason for being an are called implication pairs. So the first pair is called CB, or sometimes BC, because I prefer the alphabets. BC, then this one BE. Okay? Does this make sense? All clear? So I'm gonna write this down here. So the first part, which is we have BE, then we have here BC. We have two implication pairs. Let's go to other block, which is BC. Here is B, here is C. B between C and E, and C between B and E. So let's make a comparison. This is EE, that's fine. B is the same as the other state, C is the same as the other states, then that's fine. Then there's no implication pair. Therefore, we can guarantee that B and C are equivalent to each other. So I'm going to put a check mark on it. So we can guarantee that B and C are equivalent. So what I'm going to do, put the check mark. Okay? So here, when I put a check mark, here I'm 100% sure those pairs B and C are equivalent to each other. So our target in this implication table is to find all of the equivalents at once. We will not do the first one and redo it again and again. So we'll do all of the simplification at once. Then the remaining block, D and E. So here is D, here is E, this is the remaining circle. So this is between D and B, this is between E and A. So we realized both, or let me see, which is D the same as the state itself, E the same as state itself, therefore these two are fine, this pair are fine. Okay? Clear? Now look at A and B. A and B, those are not the same as state itself, or not the same as the other states. Therefore, this is called implication pair. This is called AB. Then I'm gonna redraw it here. A, B. Okay? Now, step number 4. I'm gonna write it here. Step 4, cross. Look at the pairs. If there's anything's being crossed, then we will cross it. So, cross the implication pairs. What does this mean? Implication pairs. We have 4 blocks. So we have one, there's check mark, then we need to look at the three blocks. Look at this one's called BE. Okay? This pair is called BE. Look at B, look at E. Where is the intersection here? Is it crossed? Yes. Since it's crossed, then we can exclude this, BE. Then we can exclude this one by making this job. It's not all crossed, like half crossed, because they're the same outputs, but we exclude this. It guarantees that we are excluding this. Then how about A and C? A and C, there is BE, and we already said BE are not the same. Therefore, we will exclude this, which is cross this one. Then the last one, A and B. Let's look, here is A, here is B. Is it crossed? Yes, it's already been crossed by this one. This is make it crossed, it's already been crossed. Therefore, we will remove it. What's the remaining pairs? Which is B and C. Therefore, we can say B and C are equivalents. That's how we figure it out. This is not the end. Don't say B and C is equivalent. Don't forget to substitute this. So I'm going to draw it here. This is the last step because I didn't have enough space. So step 5 and the end. And last one. I'm going to say that C equal to B. That's what we got. Then I'm going to draw the state table. replace every C by B. So here is states, here is 0, 1, here is X, state A, B, remove C, then we'll go D, E. So A will be with C and 1, then I'm going to call it B because we replace C by B. C over 1, B over 1, here is B over 0. This is C, it will be replaced by B, so it will be B over 1. Here is E over 0. Then here is D over 0, B over 1, remove C. Here is E over 0, A over 1. Then that's it. Is it clear? Any question? Let's do another example, so it can be much easier to follow. So we have A, B, C, D, E, F, G, H. So we have a lot of states. Then doing this by inspection may be harder. How we can do it by using implication table. Start vertically from B to H, horizontally from A to G. So vertically remove the first one, horizontally remove the last one. So I'm going to draw, here is B, C, D, E, F, G, H. Then here A, B, C, D, E, F, G. Don't draw H. Then do it like this way. Here is A. Here is for B. C. O. D. E. F. G. Okay. Then here is state 0, 1. I'm going to draw the outputs. Again, you can monitor from the state table, but if you want to draw the outputs, it's up to you. I feel myself very comfortable drawing the states with the outputs alone, so it can be easier to compare A, B, C, D, E, F, G, H, I think. Yeah. Then here's 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 1, 1. Then we can make the comparison. Here is A, here is B. A 0, 1, B 1, 0. They are not equivalents. Then cross it. They are not the same. A and C. A and C. Here is A, here is C. They are not equivalent. Then cross it. D, A and D. Here is A, here is D. They are equivalents. Then keep it. A and E. Here is A, here is E. They are not, then cross it. A, E, cross it. A and F. Here is A, here is F. They are not the same, then cross it. Then you can look also G, cross it, with H, cross it. So we can make it faster. Then the rest will be crossed. F, G, H. Now look at B. Here is B. B with C. Here is B, and make sure. Let's see if there's any similarity. With C, no. With D, no. With E, yes. With F, actually B, yeah. With F, no. With G, no. With H, no. It's only between B and E. So whenever we draw between B and E. B and E, keep it. Here, I'm just like to do it in a fast way. Now C. C with D. E, F, G, H. Here, C, 0, 1. Where is the similarity? Only between C and F. Otherwise, they are not similar. So C and F will be, which is this block, will be empty. The others will be crossed in this column. This cross, C and F not. This cross. Okay? Now with state D, here is D, then between E, F, G, H. Here is D, E, F, G, H. Is there any similarities? 0, 0, 1, 0, 1, 0? No. Then cross everything. Cross all of this column. Then we have E, F, G, H. Here is E, 1, 0. Here is 0, 1, 1, 1, 1, 1. They are not similar. Therefore, cross all of this column. Okay? Then F, G, H. F, 0, 1. Here is 1, 1, 1, 1. They are not similar. Then cross it. Okay? The last one, G11, H11, they are similar, so don't cross it. So we are done with the step number 1. Okay? Clear? Any question about this one? Now let's go to other one, which is by looking at the states. The next states. States, here, again, I prefer to rewrite them. But it's up to you. If you don't want, you can go back to the original table and make this comparison from the original table. So here it is E, D, A, F, C, A, and oh, I forget D. Forgot D. D, E, F, G, H. So in D, D between BA, E between DC, F, CD, G, H, G, H, CB. Now, how many squares uncrossed? We have 4 blocks or 4 squares, 4 blocks. Identify these blocks. These blocks are A, D, B, E, C, F, and G, H. So what I'm going to do, same way like at what I did last time, look at A and D. So A between ED, D between BA. So by looking at this one, EBBA, this can be implication pair. This one is the same as the other states. Therefore, the AD are not implication pair, right? So the implication pair that we have, BE. So what I'm going to do is go to this block and write BE. BE. Let's go to the next one, which is the block BE. BE is B between AF, E between DC. So we realize that both are implication pairs actually, and we prefer to write them in the alphabet, so it will be A, D, and CF, alphabet order. So go back here, write A, D, CF. Here is A, D, here is CF. Then the next block, which is CF. CF, C between CA, F between CD. So we realize C and C fine, but what causes the problem is A and D. Then this is implication pair AD. Then I'm going to write AD into this table, this block. Then the last one, GH. GH. G between HG and H between CB. So we realize that both are implication pairs. So we have GB and we have CH. So we can go there, GB and CH, write GB, CH. Or actually alphabets, B, G, CH. Okay. Then now, step number 4, look at the implication pairs and try to cross these blocks. Here, BE. Locate B, locate E. Is it crossed? No. Then don't cross it. Here, AD. Look at A, look at D. Is it crossed? No, don't cross it. Here, B, CF also. Let's look at CF as well. C, here is F. Is it crossed? No, don't cross it. Here is AD. This one, AD. Here is A, here is D. Is it crossed? No, don't cross it. Then BG, here is B, oh, here is G. Is it crossed? Yes. Therefore, we will cross that one. After that, there are 3 blocks are uncrossed. What we're going to do, look at the implication pairs, or look at these blocks, actually the location of those blocks. These blocks are AD, that's uncrossed. Let me mark them with the green. AD. Then we have BE. Then we have CF. So as a result, since we have uncrossed blocks, we can say, I'm going to write it here, 3 blocks uncrossed, which are AD, BE, CF. Therefore, we can say A equal to D, B equal to E, C equal to F. That's it. Then all of these 3 states can be reduced. So how can we rewrite the table? I'm going to rewrite it here because I don't have space. So we said that A equal to D, B equal to E, C equal to F. It's up to you. Do you want to remove A or D? You can choose either one. Do you want to remove B or E or C or F? It's up to you. I'm going to remove A, B, C, then keep the other table. So we have state here. Then here is X, 0, 1. I'm going to remove A, B, C, then it will be, we'll start with D, E, F, G, H. Now, with state D, we'll go to B0. B is actually E, so E over 0. Then A over 0, A is actually equal to D, then D over 0. Then we are done with D. Let's go to E. E, D over 1, then C over 0. C is actually F, then it will be F over 0. Then how about F? C over 0. C is actually equivalent to F, so it will be F over 0. Then D over 0. D is, which is, we have D, then D over 1. G, H over 1. G over 1. Then H, C over 1. C is equivalent to F, so it will be F over 1. Then B over 1, B is equivalent to E, then it will be E over 1. So that's how the table, reduced table, will look like. So then we have converted this to this. Okay, does this make sense? Any question? Now we have another example, which is kind of complicated like this. How can we make the implication table on this one? We have multiple inputs, but that's fine. Let's do the implication table. B, C, D, E, F, E, F, G, H. Here is A, B, C, D, E, F. I think I need to put them down. Okay, here's A, B, C, D, E, F, G. Here is A. Here is B, C, D, E, F, G. Then let's start crossing. Look at the outputs for each one. So A and B, 0, 0, 0, 0. Look, is there any other 0, 0, 0, 0 here with other states? 1, 0, We have D the same, we have F the same, G the same. Then D, F, G don't cross them, while the rest will be crossed. D, this D, F, G don't cross it, the rest will be crossed. Then let's look at B. B, which is 1, 0, 1, 0. Then is there any 1, 0 here? 1, 0, 1, 0. Yes, we have with C. 1, 0, 1, 0. We have with E. 1, 0, 1, 0. We have with H. C, E, H, don't cross them while cross the rest. C, E, H. C, don't cross it. E, don't cross it. H, don't cross it. Then let's go to C. C is 1, 0, 1, 0. Then here is 1, 0, 1, 0, which is at E, 1, 0, 1, 0, H. Then to cross E and H. Then to cross it with E and H. Then let's go to D. 1, 0, 0, 0, 0. Then the only we have with F, G. Then to cross it with F and G. Then to cross it with F and G. Then to cross it with F and G. Then that's it. Let's go to E. E, 1, 0, 1, 0. Then we have only with H. So then to cross it with H. Then to cross it with H. Then let's go to F. Here is F. 0, 0, 0. Then to cross it with G. Just with G. Then to cross it with G, while it will be crossed with H. Now G and H are not equal, then cross it. Okay? Then let's look at the states. We have a lot of blocks here. Let's look at how many blocks we have. AD, then AF, AG, then BE, then BH, CE, CH, DF, DG, EH, then FG. Okay, we have a lot. Let's try to compare for A and D. A and D, we have D, D, F, A, C, D. It will take some time. D, D, F, A. Here it will be D, B, A, F. So look at these, they are fine. B and D, these are implication pair. A and F, complication pair. A and F are complication pairs. So as a result, there will be AF and BD, two implication pairs, right? AF, BD. I'm going to write it here. AF, BD. Then let's look at A and F. Here is A, here is F. Here is F. D, 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 AF implication pair, AF implication pair. So AF are the implication pairs here. Only AF. Then the other one, A and G. Here's A, here is G. So we have DG as implication pair, DG implication pair, AF, AF, A, and fine. Those are fine. So as a result, we have DG and AF, two implication pairs. So I'm going to erase it to write it like DG and AF here. Now with BC, look at B and look at C. Here is B, here is C. CC, DD, EE, we have AF implication pair. So the only implication pair here is AF. Then we have BE. Look at E, look at B. C, then we have DF, EE, AF. We have AF and DE. AF and DE. Then let's go to BH. Here is B, here is H. C, B implication pair, D fine, E fine, AF implication pair. So AF, BC. Then let's do it. AF, BC. Then, it's gonna take some time. CE, after doing the analysis, let me write the final step because we're running out of time. DE, then here it will be BC, here it will be ED, or the same as DE, doesn't matter. I think, let me do it. I apologize, this is DF. This is DF. Then here is BC. Here is DE. Here is BG. AF. Here is BC. DF. Here is DG. Then BE. Then we need to look at the states and to cross everything, which is, let's look at A and F, D. Okay, I think when you look A and F, D, this is A, this is F. This is A, this is F, then they are actually equivalent to each other. So let me make a correction here. There is a check mark here. Okay. Then look at here. AF is not crossed. B and D, they are crossed, therefore cross it. Here, this check mark here. AF is not crossed. DG, here is D, G, they are not crossed yet. But let's look at DG. AF is not crossed, but BG is crossed, therefore it's crossed, therefore this one's crossed. Then AF here is not crossed. Here AF, DE is crossed, therefore it will be crossed. Here BC, AF is not crossed. Actually this one will be AF alone, which will not be crossed. Here BC is not crossed. Then DE, here is D, and here is E, this is crossed. So what else? Here is BG, BE. BE is already been crossed, we already mentioned about this. BC is not crossed, but DF, here is D. Here is, here is D. Here is F, they are already crossed, therefore we will cross it. Where is it? Here. So as a result, we will get the uncrossed blocks. We have AF, uncrossed, AF, A with F, and B with C, then C with E, yes. So as a result, A equal to F, I think this is C, C with H, I forget why I wrote E, C with H. A equal to F, B equal to C, C equal to H. Then you can redraw this reduced table. It will look like this one, because again, A equal, or we can say F equal to A, C equal to B, H equal to B. So it will be like states. Here is x1, x2, 0, 0, 0, 1, 1, 1, 1, 0, A, B, D, E, G. So it will be here D over 0, D over 0, A over 0, A over 0. This will be B over 1, D over 0, E over 1, A over 0. D will be D over 0, B over 0, A over 0, A over 0. E will be B over 1, A over 0, E over 1, A over 0. Then G will be G over 0, G over 0, A over 0, A over 0. And that's it. Any question? Okay, let's end up the recording.